Hello, my name is David Ackerman, student number 220-310-629, and this is my Quiz 2 Summer 2025 submission for MEC 3409 Machine Element Design. Let's get started. Here we have the Quiz 2, my name, student number. Quiz 1, this is the question, this is a diagram that we're given, and these are the answers that we have to give, or the questions that we have to answer. So my student number is 220-310-629, which makes x2 and y9. The shaft properties are Young's modulus is 207 GPa, which converts to 207 times 10 to the 9 pascals. The density is 7,775 kilograms per meter cubed. The length is 800 80 centimeters, which transforms to 0.8 meters, and the diameter is 3 plus x plus y, which is 3 plus 2 plus 9, which equals 14 centimeters or 0.4 meters. The analysis is the gear forces are given by those equations, which when you plug in the x and y, they are the F1 is 206 newtons and the F2 is 780 newtons. The shaft properties, now it's the area is given by that formula, which you plug in when you plug in my D value, you get that it's equal to that value. The moment of inertia is pi divided by 64, diameter out to the power of 4, which you get this value right here. The total mass of the shaft is given by the pressure times the area times the length, which you plug in all the known values. The only one that varies is the area. These two were given, and you get this in kilograms. And the influence coefficient you are given by this formula for 0x x is greater than 0, which is less than a. We are then using this formula right here, which is equivalent to this one for 0, and we're substituting in L for x equals to make this x equals greater than 0 and less than L. So now we're solving for part A. So the deflection happens right x when x is at A. It's under load. So the gear's locations are located from the left support. So the gear location at A1 is 20 centimeters, which equals to 0.2 meters, and gear 2 is located at 0.4 meters. The influence coefficient is given by this formula here, which is essentially the same thing as that. You plug in all the values, and we get that influence coefficient deflection of gear 1 due to the unit load at gear 1, and this is the deflection at gear 2 due to unit load at gear 2. So 1, 1, 2, 2. These are going to be important values later. These are going to be deflection of gear 1 when unit load at gear 2. Use the deflection formula for x, it has to be a equals 0.2 and a equals a2, which is 0.4. Plug in all those values, and you get a gear 1 at 2 is 4.269 times 10 to the 8, and Maxwell's property theorem, meaning that these two are equivalent. So those are our answers for part A. For part B, estimate the first critical speed with the principle required. This is the formula given, and we're going to be using this throughout parts. The W1 and W2, gear 1 and gear 2 critical frequencies, and the WC shaft, or the distributed mass of the shaft. The single mass critical frequency is given by this formula, where that's the static deflection due to the weight of the mass. So the gear 1, we have to find the mass, which is that we just use the F equals mg equation, and we rearrange for m. You do that the same for gear 2. The gear 1 critical speeds, the static deflection, which is given by um, alpha 1, 1 times the force 1. We plug in, we get that number. The frequency is given by this formula that we plug in the static deflection that we previously calculated, and we get the critical speed 1, which is this number. Same thing for the gear 2 critical speed, but we use the alpha value for the gear 2 speed only, and we use the force for the gear 2. plug that into the formula, that the critical speed for the frequency for the frequency for the second gear critical speed, and then we get this the shaft only, which is given by this formula. We plug in all the known values, we get the critical speed for the shaft, and then we plug in all of those. We have to take the reciprocal and make sure to square it, and we get this value right here. And convert to RPM. Yeah, sorry, I blanked out there for a second. Converting to RPM, we just multiply by 60 divided by 2 pi. And we get this value right here for NC to RPM. So for part C, the max operating speed should be 75% of uh, the NCD. So when you multiply this number by N max, you get 3,641, which should be the new operating max speed. Part D, the is that gear one and two are swapped. The positions are swapped. So gear one, the force one is now at A2, and gear two, force at F2 is now at A1. The new critical speeds for the individuals. So um, this is the new critical speed for gear one at position A2. You calculate same thing. Um, but this one, you're taking the alpha value for the second gear times, because it's at that location, divide times the force at gear one because it's at the second location of gear one, as the location of gear two, but with the force of F1, and you get this value. You use the same, the formula is the same. You just plug that into this formula here, and you get the new value for the critical speed of C1. Same thing for the uh, new critical speed for gear two at position A1, that they switched gears, but the alpha value has to be used for position one. So the alpha values for position one times force of gear two, you multiply both of them together, you get this value, and you plug it back into the critical speed of frequent two. And now the speed of the shaft is should be uh constant, the same. So you plug them in, you equate all of them, you square it and take the reciprocal of it, and you get the critical speed. The new critical speed CD is 556. Convert to RPM, same thing. You multiply by 60 divided by 2 pi. And now the new max operating speed is the same thing. You have to take it by 0.75. So the new max operating speed when the gears are switched is 3,982.34 RPM. This has been my video. Thank you so much for listening.